Hey everyone. So I'm back, this time during the day. Halo of light coming in through the window behind me as a big clue to that. Um, in the previous video, I finished off with mentioning that I might go into discussing torque, which is a rotational force and helps us to understand what's going on in terms of joint motion, when there's an axis that we can identify, and that's very, very important for understanding exercise and what's going on whenever we're trying to lift a weight or when we're dealing with pulleys or anything like that. But before getting into that, I thought about it and realized that it would probably be a good idea to go back to the beginning and look at Newton's three laws a bit and understand especially inertia and mass, because understanding mass helps you to understand momentum and kinetic energy and work being done on objects. These are all concepts that we want to understand if we're trying to describe how motion works when we're lifting weights or moving things around. You need to have an understanding of what mass is first. So it feels like it's important to go back and establish that, fill in that gap. So that's what I'm going to do today. And then I'll briefly go into maybe a little bit about velocity and momentum, talk about vectors and scalars. We'll see. I don't want to make this too long. Okay. But Newton has three laws, came up with three laws. That's Sir Isaac Newton, kind of a smart dude, kind of important. And they're often called Newton's laws of motion. This is an oversimplification. There's a lot more that the man did. There's a lot more to these laws, but I'll give you the basic breakdown, right? The first one is simply called inertia, which is saying that an object at rest will stay at rest, or an object in motion will stay in motion and have constant motion unless acted on by an outside force. So if you imagine there's some little object floating along in space, let's say it's floating in a straight line. Well, if there's nothing else acting on it, nothing tugging on it, pushing on it, it'll just keep drifting along in that direction at that speed forever. Okay? Now, realistically, there are always other forces to consider, but bear with me for now. If an object is sitting stationary, so if I set this little pen, this marker, on my computer desk right now, if I don't do anything to it, if nothing changes and there's not like an earthquake or something to shake it around, it'll stay right there on the desk indefinitely, because there's no net force acting on it. Gravity's pulling it down. Gravity's a force, but the table's also pushing up on it. And because those forces are balanced, this object is not accelerating. Its motion is not changing. It is in a constant state of motion. It has a constant velocity of 0. Okay? So that's what inertia is talking about. I'll come back to that. Our second one that we have, and I'm not going to spend too much time on this today. Number 2 is force equals mass times acceleration. And if I want to really be accurate here, I would put these little, it's supposed to be chisel tip on this thing. Put a little arrow over force and a little arrow over acceleration. Why did I do that? Because force and acceleration are what we call vector quantities. And that means that they not only have a number associated with them, 6 pounds, 100 meters per second squared, but they have a direction. They have an orientation, a bearing associated with them. So 10 pounds downwards, 100 meters per second squared to the northeast. We have to fully understand these values, we have to have some sort of a direction associated with them. So they are defined as vector quantities. So anytime you hear the word vector, that's what we mean. In fact, I'll put that off to the side right here. Okay? So we have something that's called a vector quantity. So vector means there is a magnitude. I'll just put mag. So the amount of the thing. So how many pounds, right? It also has a direction. Okay? We'll get more into that a little later. But we need to know, is it pushing this way? Is it pushing that way? If somebody pushes on you, it matters where they're pushing on you and what direction, as far as, what direction you might move in, right? If I push you in one direction, you're not going to suddenly accelerate in the opposite direction. You're going to accelerate, if at all, in the direction I pushed on you in, right? Number 3, Newton's third law, is something we call action-reaction. I'm going to abbreviate it this way, AXN/RXN. But all this means is that for every action, there is an equal and opposite reaction. In the context of forces, it's really what this is talking about. If I push on something, that something is going to push back on me. I'm sitting in my chair right now, and the chair is pushing back up on me with an equal force in the opposite direction. These forces, again, forces are vector quantities, so forces have a direction associated with them. Those forces cancel out, right? Because they're in opposite directions. So if you add them together, they add up to 0. That's why I am sitting in this chair and not accelerating up or down. If forces were not balanced, that would not be the case. But I don't want to get ahead of myself, okay? When we start doing free body diagrams, if I do that, things can get kind of tricky and confusing, so I don't want to move too fast. The basic idea behind this third law is action-reaction. Just that there's going to be a pushback on me anytime I push on something, okay? Anytime you push on a thing, it has to push back on you. You cannot avoid this, okay? So those are Newton's 3 laws, and buried in those laws are implications for all kinds of things. All of the motion that you and I go through, we can explain, generally speaking, with some manifestation, some version of these laws, or things that we derive from these laws. Okay? I'm not going to start talking about relativity. That's another discussion that doesn't really impact us too much when we're just working out at the gym. Let's come back to inertia. I said before that inertia is an object's resistance to a change in its motion, right? Well, what do we know about mass? I'm going to relate these two. Mass is the amount of stuff in an object, right? And if we look at Newton's second law just for a second, well, for a given force on a given mass, we're going to get a given amount of acceleration. If the mass gets bigger, this acceleration has to get smaller if we don't change the force, right? So if I'm pushing on something with 100 pounds, I can accelerate a certain object of a certain mass a certain amount. If that object gets twice as big, well, I can only accelerate it half as much. This side of the equation, if I'm not changing the force, this side of the equation will need to remain the same. Okay? So that's basically saying that mass tells us something about how much an object can resist a change in its motion. Well, we just said that inertia is an object's resistance to its change in motion. So really, inertia and mass are very tightly related. You could say that mass is a numerical representation of inertia. I'm going to use a different color marker here, and I'm just going to draw an arrow here. Like, inertia relates to mass! Exclamation point. I want you to draw a link in your mind between these two things. So the amount of stuff in an object, it's what we often are first told mass is. That's not wrong, but in a more pure sense, why that matters is it tells us how hard it is to move that object, how hard it is to accelerate it. The more mass there is, the more resistant it is to a change in its motion. When I drop an anvil on someone's head, not that I would ever do that, but if I were, why is that very dangerous? Well, because it has a lot of mass. But what's that mean? Well, it means that when it falls on your head and your head is pushing back up on it, your head has to push back up on it really hard to stop that thing from moving downwards. And based on Newton's third law, for every action, there's an equal and opposite reaction. If your head's pushing up really hard on that anvil trying to stop it, well, that anvil is pushing really hard on your head. So, that's why heavy objects, when they fall on us, hurt. It's one way of thinking about it anyway. So hopefully that makes sense. So I just wanted you to think about that. Inertia and mass are very tightly related. And we're going to talk about mass when I start talking about kinetic energy, which is the energy of motion of an object or a system, as well as momentum. And momentum and kinetic energy, they're not the same thing. There are relationships between them. I will briefly mention these just as a teaser for maybe the next video. Momentum is, we can think of as the total, I'll put quotation marks, the amount of motion the amount of motion an object has. How many total moving particles are there, and how fast are they moving, basically. So that's how we define momentum. We abbreviate it in physics with P. It's also a vector because it has a direction. Okay? P, or momentum, equals the mass of an object, so M, I'll put a dot, times its velocity. So, if I have a certain object of a certain mass, let's say I have a baseball, and I throw it at 50 miles an hour, it's got a certain momentum. If I throw it at 100 miles an hour, it has twice as much momentum. No, I cannot throw a baseball 100 miles an hour. My fastball is not nearly that good. I would destroy my shoulder trying. But hopefully that is reasonably easy to understand. Okay? So that's momentum. I will save energy for another time, but when we start talking about these concepts, we need to have an idea of what mass actually is. Okay? Before we can really talk about these objects that are moving, what's happening in a moving system, when a weight's being lifted, when a pulley's being pulled on, or when it's pulling back on you. And I'll slowly try to explore these other concepts in more detail. Okay? Hopefully that made some sense. So we have inertia. Inertia is very closely related to an object's mass because they both express how hard it is to move an object. They're both dealing with this concept that objects have a resistance to a change in their motion. Okay? I briefly talked about vector quantities. A vector is simply some quantity that has a magnitude, so there's an amount to it as well as a direction. And I will go more into vectors next time and compare them to scalar quantities, okay? So hopefully that was helpful. Let me know in the comments. Give me a shout. Tell me I'm terrible. Whatever you need to do. Stay tuned.